Okay, I got my pen. And we're gonna finish up chapter 21 with one big activity. Starboard. This is one we did last time. There was a nice overlap with the phenol sequence here. There's a phenol in all of these, and phenols are cool. We already know they have a cool pKa, 10, and now you're learning they can be used to put groups onto benzene, whether it's in the Claisen rearrangement, oh yeah, that's an R, or in the Kolbe synthesis. And I'm hoping somebody can tell me the name of just this piece. Somebody in this room, yeah, somebody in this room should know the name of that piece. And what is it? Orthohydroxybenzoic acid? No. That's one of its names. How about phenol orthocarboxylic acid? Also its name, but it's called salicylic acid. And Kolbe's the guy that changed history. Not the basketball Kolbe, this Kolbe. Salicylic acid is used in a lot of medicines. By itself, it's a medicine. It's a pain reliever. It causes stomach issues, serious stomach issues. You can't take a pill. But it's also a disinfectant and it penetrates into oily areas. So salicylic acid can be applied to blemishes, and it gets underneath the oil and gets to the infection, and it kills it. It's also used to make aspirin, acetylsalicylic acid. So very useful. Until Kolbe's day, all of the salicylic acid was obtained by extracting it from the bark of a willow tree. And that means you had to strip the bark off the willow tree. Guess what the outcome is for the willow tree? Lumber. Okay, you had to kill the tree. Sad. We don't like doing that. Okay. So phenol, which is right over here, is where you started, is pretty cheap. It's a byproduct of the petroleum industry, and they don't like putting it in your gasoline, so they're looking to sell it to people. And it's good for synthesis, so a lot of chemical companies buy up the phenol. And salicylic acid has the phenol on it still, and we're doing oxidation to a quinone here. That's a new thing at quinone. Paraquinone. That's right there. Paraquinone. You know why it's para, right? So this is all about mechanisms. I didn't quite get set up for today. Okay, we're set up now. Ish. KOH is a base, you know that. Lone pair, minus charge, grab the H, make a phenoxide ion. Phenoxide. Phenoxide comes from phenol. Phenol's the main player on this page. Just a good old SN2 reaction gets you to the first drawn molecule here. Switch to red, sorry. Then the Claisen rearrangement is actually in this step here. This was just the setup step. The first step was the setup. Remember, it has to be an aryl, allyl, ether, or the Claisen rearrangement can't happen. Aryl is an aromatic ring. Check. Aromatic ring. And allyl means C-double-C, and then the O is on the next carbon. Allyl. Arrows look like the resonance of benzene. What do we call mechanisms where the arrows look like the resonance of benzene? Mechanisms where the arrows resemble benzene resonance. You remember what those kind of reactions were called? Started with a P, ended with a C. Yes. Pericyclic. Uh-oh. I gotta move that C. I hope it lets me. Yes, thank you. Pericyclic reactions. Yeah. Others being beta decarboxylation, and in the lab we do the Diels-Alder reaction. There's also other cool reactions. One's called the Ene reaction. We're not going to get to that. There's a lot of cool, good stuff. Kolbe synthesis. Well, once again, we have KOH, so what you did the first time works again the second time. I apologize, I didn't show the H bonded to the O. I'm fixing that right now. Crossing off K, put a lone pair, put a minus. Attack the O, that's H, sorry. Dump the electrons on the O. We're gonna call this thing R for the rest of the day, because it never changes in all these steps. Where'd the O, they get the H from? Oh, we didn't finish the mechanism for the Claisen rearrangement. That's where the O got the H from. No, that the arrows I gave don't give that product. I was just so excited I wanted to move on. Huh? There's an intermediate. I'm glad somebody asked that question. This is going to be a ketone, isn't it? Ketone. And since we labeled R, we got R. I want to remind you there's an H on this carbon. There's the old double bond there and there. And what do you call that reaction? Yeah. They had trouble in lab remembering that reaction too yesterday. Yeah. What's that called? Ketone becoming enol. Yeah. No? Yeah. Tautomerization. Now there's no chemicals here. So you can't use an acid catalyst, can't use base catalyst. What's the third option? You got to do the proton transfer between two identical molecules. Intermole. So let's have an arrow going to the H, and then this going here. But the arrow going to the H can't reach. It's getting a little tight here. Trying to blow it up for you. On that first arrow, I need to write intermole. Intermole. Mole. Trying to get a nice E there. There you go. Intermole. Tautomerase. And then we started the Kolbe synthesis. think we're gonna go this way. Zoom. Here's the Kolbe. And we're gonna get a phenoxide again. This time our phenoxide has an R group on it. Phenoxide number 2. What'd you do with it last time? You did an SN2 reaction. But if you do an SN2 this time, you're going to get a group on the oxygen. Do you want a group on the oxygen? Take a look. I don't want a group on the oxygen. Where do you want the group? Where's the new bond? Ortho position to a carbon. Where'd that carbon come from? Yes, CO2. Hey, attacking the carbonyl with an anion, that's an enolate. Oh, you didn't see that, did you? Phenoxide is an enolate. Yeah. So I got to resonate and then use the ortho position on the left side. So I'm going to resonate all those pi electrons with the O minus. Here goes. You ready? Bring it down. Resonate. Resonate. Attack. What are we attacking? You said it already. CO2. CO2 is going to become CO2 minus. Take a look at that. It's got to be the coolest thing ever. Ketone. That's not going to stay. Now we got a double bond there. We got a double bond there. I got to remind you, you have an H here. It's not in the product. That's why I drew it. O minus, double bond. Mm-hmm. Yeah. I'm going to cut you some, do a favor here. Comma, I'm just going to say in step 2, there's still OH minus. Just to make your life a little easier. Add that in there in step 2. And I'm going to add it at the top of the screen. Sorry. Comma, OH minus is here too. I'm just trying to make it more similar to the one in the textbook. So I can see how I make this into a benzene again. Right now it's not aromatic. And I'm going to make it aromatic. There's a word for that. Taking something that wasn't aromatic and making it aromatic again. Oh, that doesn't need to be black. Oh, I'm going to get rid of everything if I do that. That's not. You tell me how to get there. Keeping in mind, there's OH minus present this time. Yeah. Yeah. And then resonate up to the carbon, to the oxygen. Grab the H, resonate, resonate, and you're done. And I lost my R group twice, didn't I? This is a salicylate. Okay. A salicylate. Where are we putting names of molecules? Blue. A salicylate. Needs to become a salicylic acid. Hey, look at step 3. We'll do that in hot pink. Now, step 3 is going to there. Is that right? Yeah. You can do 2 reactions with HCl, but I do expect you to know which is first based strictly on pKa. You're about to make a phenol. What's the pKa of a phenol? 10. You're about to make a carboxylic acid. What's the pKa of a carboxylic acid? 5. That means the base to make the phenol has a pKb 14 minus 10, because you already told me the phenol is 10, right? That's 4. And the pKb to make the carboxylic acid, 14 minus 5, is 9. Which one is 100,000 times stronger? The 4, pKb 4 for the phenoxide. I want you to tell me, you know, phenoxide reacts first, and that's an easy one, right? Red first. And here it is, phenoxide first, strictly based on pKa. We'll go with green for the carboxylate, becoming the carboxylic acid. And we are done with the Kolbe synthesis. And it's a beautiful thing. And we've got another activity underneath. Big picture here. We're going to do oxidation to a paraQuinone. And it looks like the two things really happen. There's an oxidation for sure, the carbonyl at the top. But there's a new oxygen on the bottom. Where the heck did that come from? Take a guess. Don't take a guess. Let's do the mechanism. Or maybe you want to take a guess. You want to take a guess? Where'd the new O come from? This one? Here's your choices.
From water.
From water. Thank you. The one closest to just oxygen, right? It's not the first time we've seen an O show up where there's an acid present. I think we need a carbocation to put the O on there. And I think we're going to just pretend we're doing an oxidation like normal on the top oxygen, because that's an alcohol, right? And maybe there's a way we can put a cation on the bottom carbon when we're making that ketone. Let's see. What is the first step in all chromic acid oxidation? There's a hint. Activate the oxygen on a chromonyl towards attack by an alcohol. Here's the alcohol coming in green. That arrow didn't look good at the end. We need to blow it up a little, that's why. There, that'll look better. And we got to say green. I'm just going to reiterate red first, green second, because I'm going to do a purple too. I'm scribbling this H off. I'm going to put it on over here. And you made sulfate ion during this exercise. OSO3H negative, which can come in purple and neutralize our oxonium, which is something you need to do. Red was first, you had to activate the chromonyl. Green's first. Why did you activate the chromonyl? To make it more reactive towards an alcohol. That's why green is second. You just generated an oxonium. Now you're allowed to take the H off the alcohol because it'll be an oxonium, a strong acid. So you can take the H off. And the result is the precursor to a chromate ester. The precursor. It's got a double bond on top. It's got an OH to the left. It's got a new OH on the bottom. In fact, that one I'll show like that. And it's got an OH to the right. And I'm missing a lot of stuff. We're allowed to call this thing R. We circled it elsewhere. And we still have double bonds there. Hi. Double bonds everywhere. Do those again. Double bond there, double bond there, double bond there. CO2H on the left. He's just hanging around. That's almost a chromate ester. If I get rid of this and this, it will be a chromate ester. What do you call it when you remove HO and H? Dehydration. You need an acid catalyst with its conjugate base. Conjugate base. Acid cat, right there. And we are going to take the H off. You could argue, you know better now. What's the purpose of the acid? To make the OH a better what? Leaving group. You could argue that should be first. And then the green would finish it off. You just made it a good leaving group. Now you're making it leave. But if you prefer one color of arrows here, because it's in chapter 10 like that, I will accept it. Okay? Chapter 10, the protonation's happening as it's leaving. It's not as accurate, but it's in the book. Okay, where we got? Chromate ester. That's when you're allowed to think about oxidation. CrOOO. Doesn't it look a lot like chromic acid? Yeah, chromic acid, chromate ester. It's the same, except instead of an H here, there's a carbon. And we got an R group and a CO2H. R changes color, sorry about that. You get a cation on that bottom carbon right now and a ketone on the top. Only using the chemical that's drawn right here. 1, 2, 3 arrows. I need a cation on the bottom, so I gotta push away from the bottom. That makes a carbonyl. That don't need to use anything. I got this. I got a carbocation. Oh, start over. Didn't change that. Got that. We got a carbocation right there. Got a carbonyl up here. Got HCrO3. Then we got R and CO2H. Hey, I need to get a second alcohol down there so I can then oxidize it the normal way. No twists in the next oxidation. And you notice in the last 5 exams, this mechanism shows up every time. 6, probably not an exception. Okay, won't be an exception. How's that? So what's next? Got to get an alcohol down there. Water attacks, and you're going to use the base of sulfuric acid after it's attacked. Oh, yeah, that does the job. There's a minus here. Green. So now you got another phenol. Well, it's not really. There's no benzene. Same story on the chromic acid. Yep, I want it again. Yep. And HOSO3H Starting over. Lone pair protonates first. Alcohol comes along, attacks the chromium. Sulfate ion comes along. I'm just making dots on my page. Okay, sulfate ion was made here. You can write it here. OSO3H negative. And purple. Yeah. Oh, I forgot my carbonyl. My goodness. Okay. What do we got? We got a lot of stuff. Carbonyl, double double, double trouble. Oh. See, oh, we did a huge shortcut. No more shortcuts. I already got it. 3 steps in one. And we don't have a chromate ester yet, but we're going to have one really soon. Don't forget R and CO2H. Okay. We're almost there. Epic. This is a double activity for sure. Maybe triple. What do you think? Triple. I got to make that into the chromate ester number 2. Well, that's dangerous trying to do that. Worked. Okay, chromate ester number 2. CR0000 OH. And a reminder, there's an H over here that's not in the final product. Okay, so how do we get there? Well, how did you get there last time? You had the chromium with 3 OHs on it right here, didn't you? Chromium with 3 OHs on it right here. We need the base and the acid. Acid catalyzed dehydration. So here's the base. HO3SO minus. Here's the acid. Maybe I should have put it above. HOSO3H. Base grabs H just like before. Sigma becomes pi just like before. Oh, but we want to be a better student than before. So we say, oh yeah, really, you should protonate it to make it a better leaving group first. Then the other stuff comes in green. I want to be consistent. Okay. And then it's just traditional oxidation to get to the product. The product's up there. Yellow is unobtrusive. We're going there now. How do I do it? Talk to me. You want the clue? Here's the clue. Other product is H3O plus. H2O attacks that H. Sigma becomes pi. Chromium gets the lone pair. That's how it gets reduced. Epic. Can't fit it on a page. That's pretty good.